We will continue our discussion on Chapter 3 with polyatomic ions and nomenclature, how to write the name of chemical formulas, or if we're given the formula, writing the ions. First of all, we've talked up to now, we've talked about how the elements in the periodic table can form ions, cations, which are positive ions, or anions, which are negative ions, but they were made of a single element. Now we can also have, so we're going to talk about polyatomic ions. From the name polyatomic, poly comes from the Greek meaning many, so we have many atoms that form the ion. So an ion that contains two or more atoms that are bound together. These atoms are bound covalently, but there is an overall charge on that whole ion, the polyatomic ion. So these are called polyatomic ions. In the next couple of slides, I have provided for you common polyatomic cations, positive ions, and common polyatomic anions. You will notice that there are a lot more anions that are polyatomic than there are cations. So here's the three that are the most common polyatomic cations. Ammonium, which is NH4+, hydronium, H3O+, and mercury 1, Hg2, 2+. Note that this charge doesn't necessarily belong to the hydrogen or the nitrogen. It's an overall charge over the whole ion. I don't expect you necessarily to memorize all these, although the more you work with these, the more familiar you will become with them, and you will tend to remember certain ones just because you will be using them quite a bit. But I would suggest that you print these tables out and that you have them handy. You need to figure out, if you're given the name, you will need to figure out the corresponding formula and the charge that goes with it, and vice versa. If you're given the formula of the ion, whether it's positive or negative, you will need to figure out what the name is for that particular ion. Here is the list then for the anions. You can see it's quite a bit more extensive. This is not actually, there are many more anions that are not necessarily included in this list, but these are the ones that we're going to use the most in our class. Once again, I would suggest that you print this out and that you have it handy to use in problems where we will need to figure out names or formulas. Now, let's talk about nomenclature. How do we write chemical formulas if we're given names and vice versa? The basic underlying principle of how to write these formulas of ionic compounds is that ionic compounds are neutral, and therefore they have to have equal positive charges and negative charges that come from anions and cations. And therefore they must contain a ratio of ions, positive or negative, that gives a neutral compound. Now this ratio of ions can be single atom ions or polyatomic ions. When we deal with polyatomic ions, consider them as a unit, as a whole unit. And if it helps you, just replace the whole polyatomic ion with a letter, keep the charge, and once you figure out the total, the formula, basically how many polyatomic ions should you have, then you can go ahead and replace that ion back to replace the letter with the polyatomic ion. And we will be doing quite a bit of these once again in class, but here's an example for you. Okay, we have a compound that is formed from the ammonium ion, NH4+, and the oxide anion, O2-. Note that this is a polyatomic ion because it's made up of more than one atom. Now, if I wrote this as NH4O, remember that the positive ion is written first, I would not have a neutral compound because I only have a +1 charge here for a positive charge, but I have 2- for a negative charge. And therefore, a +1 and a 2- gives me a remainder of a -1 charge. To balance the 2- charge, I need to have a +2. I cannot change the charge on my ion. I can't make this NH4 +2 to cancel this 2-. But what I can do is have 2 of these. And what I mentioned earlier is if it confuses you, you can make this X plus and O2- and say, well, I need 2 of these X's, and you would put a 2 as a subscript down here and then replace NH4 instead of X. Note that when you have a polyatomic ion in your formula and you have more than one of that polyatomic ion, the procedure is that you would put parentheses around your polyatomic ion, and then you would put a subscript outside of that parentheses to tell you how many of those ions do you have. So in this case, just like it is here, see that I have a parentheses around my ion, my polyatomic ion, and then outside of that I have a 2 because I need 2 of these ions. Each of the ions has a +1 charge, so if I have 2, that gives me a total positive charge of +2, and that equalizes, neutralizes, if you will, the 2- charge on the oxide, making this compound neutral. It is important that you put that parentheses if you have 2 or more of that polyatomic ion, because if you put this 2 without the parentheses, it would look as if it's NH42, and we need that parentheses to separate these 2 subscripts from each other. Remember, I cannot change the NH4. That is the formula of the ammonium ion, and I can't change the charges either, but I can change how many of that particular ion I have. An easy trick to do these is to cross the charges. So if I'm pairing these 2 ions up, I have a 2- charge here and a +1 here. All I have to do is bring this 2 over here as a subscript, so I need 2 of these, and then take the +1 and bring it as a subscript on the oxygen side, except we don't write it because it's assumed that it is a 1. Note that if the charges are equal, so if this were a +2 and a 2-, there is no need to cross the charges. You would just write NH4O if this were a +2. This crossing only happens when the charges aren't equal. A specific class of polyatomic ions is called oxoanions. So these are anions that are polyatomic, but they contain at least one oxygen atom, one or more. So if they contain at least one oxygen atom out of the 2 or 3 or however many in the polyatomic ion, however many atoms there are, if one of them is oxygen, then you have an oxoanion, which means, right, the oxo stands for oxygen and the anion is negative. Now, typically the oxoanions occur in a series. So it's not just one, they can have multiple oxygen atoms. So they can you can have two or more in one series that have the same type of atoms, but they only differ in the number of oxygen atoms. When a series of these oxo anions consists of only two, the ion with more oxygen is named with the 8 H or ATE, so the 8 ending, and the one that has fewer oxygens, it ends with the ITE or ITE ending. So here's an example of oxo anion series. These have the same types of atoms, right? We have nitrogen in both cases and oxygen in both cases. They're oxo anions because they have at least one oxygen atom out of those two types of atoms that make up the polyatomic ion. Now in this series, we have one ion that has only two oxygens, so has the fewer oxygens, and the other one has three oxygens, so has more. Therefore, this is called the nitrate with an ATE ending, the nitrate, because it has more oxygens, and the one that has the fewer, it's called nitrite. It has the ite ending. We will notice we will work with sulfate and sulfite. Sulfate has four oxygens, sulfite has three. We have phosphate and phosphite. Phosphate has four oxygens, phosphite has three oxygens, etc., etc. Let's try a sample problem. Name the following ionic compounds. Now you have three of these. The first thing that you need to figure out is whether you have a polyatomic ion. Note that here, now we've already done one of these, so this is a polyatomic ion. This has a parenthesis around it, so that means my ion is whatever's inside this parenthesis. And note that I have two atoms that make up that ion, so therefore this is also going to be a polyatomic ion, similar to this one. You will also determine whether you have a cation that forms multiple charges. NH4 only forms one particular ion. Aluminum, you're going to have to look that up, whether it forms more than one. Iron, you're going to have to once again look that up and see if it forms more than one ion. In the case of those cations that form more than one ion, then you're going to have, when you write the names, you're going to have to write the Roman numeral behind the name. Okay? A quick way to figure out what the charge is, once again, we did the charges and crisscrossed them, brought them down as subscripts, but you can also back calculate, so you can take the subscript and bring it up as a charge. So if I have a 3 here on the OH, that means that my aluminum, so I cross it to the aluminum, that means that it has a 3 plus charge. Aluminum, I only have one of these here. That means that if I cross it to the OH, that will give me on OH minus 1, etc., etc. So 3 here and 2 here. Go ahead and try this. Try and practice a little bit, and we will do, like I said, we will do many more of these during class, but you can go ahead and work on these on your own. Here's another sample problem. Now, it's the opposite here. We write the formulas from the name. So we have mercury 1 chloride, we have lead 2 chromate, potassium hydrogen phosphate. This hydrogen phosphate is actually a polyatomic ion. Remember what these stand for? These would be the charge, right, on the cation. So go ahead and try to figure out what the formulas of these three compounds are. Just make sure that at the end you figure out, you calculate that you have neutral compounds. So your total positive charge has to equal the total negative charge. To wrap up, here's a quick kind of flow chart on how to name ionic compounds. So does the ionic compound contain the ammonium ion, NH4+? If it does, then you name the compound as ammonium plus the anion name. And here's some examples. So NH4 is ammonium chloride, ammonium sulfate, ammonium nitride, ammonium nitrate. Note that if you have a polyatomic ion like NO3 and SO4, those are the names you can get from the table. But if it's a single atom anion, like Cl- or N3-, then those you will figure out from the name of the element with truncated with the IDE ending, IDE. If the ionic compound doesn't contain the ammonium ion, then you have two possibilities. Does the metal ion have more than one possible charge? If it doesn't, then it's a type 1 ionic compound. All you have to do is name the metal name plus the anion. Here's some examples. Sodium is group 1. It will always form a +1 ion. And therefore, I don't need to specify the charge. All I have to do is name the metal, sodium, and then name the anion, the nonmetal, by truncating it and adding the IDE ending. So bromide, from bromine, I cut off bromine, ing ending, and I add bromide, and so on and so forth for the rest of these. If the metal does have more than one possible charge, then I have a type 2 ionic compound. So I have to name the metal name, add the Roman numeral that corresponds to the charge, and then the anion name. The only difference between these two types is that you have to specify the charge in the type 2. And here you don't. Otherwise, they're named exactly the same. So here it is. This is iron 2 chloride because each chlorine has a -1 charge, and I have 2 of them. That gives me a total of -2. That negative charge has to be offset by the positive charge to have a neutral compound. So if I have a -2 negative charge, I have to have a +2 positive charge to make it neutral. Well, since I only have one ion of iron, only one, I don't have 2 or 3, that means that all of the positive charge resides with the iron, which means that it's a +2. And therefore, when I name this compound, I would write the name of the metal, iron, parentheses 2, because that's the charge of the metal, and then chloride, which is the name of anion. Go ahead and practice a bunch of these to get the hang of it. They're not that difficult. You just have to do a few to really cement whether you have a type 1 or a type 2, using polyatomic ions, how to figure out what the charges are. I'm also going to supplement these with some other videos of problems that I've done, and you can watch those, and then you can first try them on your own. You can pause the videos, try them on your own. Then if you want to compare, then you can watch how I solve them and then see if you've done them correctly, just so you can have some more practice with these.